In this video, we're going to work through some momentum examples. So a real quick overview, if you'll remember that momentum, and the symbol for momentum is P, don't know why, momentum equals mass times velocity. It is inertia in motion. And then an impulse is a force exerted for a time that changes an object's momentum. Note these little symbols right here indicate that they are vectors, which means you are going to have to break things into components. So there are two types of collisions we're going to talk about. One is an elastic collision, where things bounce off each other. And in this collision, momentum, your change in momentum, equals 0. This means your initial momentum and your final momentum are the same. Momentum is conserved. Now, the other thing to note is that in an elastic collision, when things are bouncing, kinetic energy is also conserved. Your change in kinetic energy is 0, so Ke initial equals Ke final. So you get these two things that you can go off of. Elastic collisions are a little different. Now, in an elastic collision, momentum initial is equal to momentum final. Momentum is always conserved in any collision. This will always be true. However, in an inelastic collision, delta Ke not equal to 0. And if you think about this, when things stick together, they look different, and that's because you're going to lose kinetic energy. Kinetic energy is going to get transferred into something like heat or just squishing things. So here's our first problem we're going to work through. A 0.3 kilogram ball goes in at a velocity of 5 meters per second at an angle of 37 degrees and bounces straight off this wall. So I'll let you pause it here, take some time to write this down, and then we'll work on it. So if we look at this, we know this is an elastic collision, so momentum is going to be conserved. That's for any collision. Your momentum is changing, which means there is an impulse. So if we look at this, we'd have to break this into components, but we can see that if your initial velocity and final velocity are the same, and this angle is the same, your y final velocities and your initial y velocity are the same. So that's not going to really help us out at all. So the only way that we're going to fix this is by looking at the x component, because no change in y momentum, no change in y force. So you know that change in p equals a force exerted for a time. So it's going to be your final momentum minus your initial momentum equals a force times delta t. So if we look at this, we know we want to solve for f, so we get m1 v1 minus m1 v1 initial over delta t equals your force. So now we just plug in our values. We get 0.3 kilograms, that's the mass, times, and in this case, its final velocity is in the leftward direction, negative 5 meters per second, sine 37 minus 0.3 kilograms, 5 meters per second, sine 37, sorry, that's off the page, but sine 37 all over 0.200 seconds. And you get your force equals negative 45 newtons. Now, all this negative is just a direction, so the total force that's being put on this ball is 45 newtons. Again, sine, go ahead and check your diagram for trig functions. Let's work another example. You have an astronaut right here. If you want to be the astronaut, you can pretend you are the astronaut. You are lost in space, you've got to throw this bag of moon rocks, and you chuck it just to see how fast it makes you go. So if we're solving this, you know that there's no external forces, so your change in momentum equals 0, meaning momentum is conserved. Initial momentum is equal to final momentum. So if we look at this, initial momentum, is anything going? And the answer is no, it's not. So initially you have 0 momentum, which means mass of the astronaut times velocity of the astronaut plus mass of the bag times velocity of the bag. So momentum of the astronaut plus momentum of the bag equals 0. So if you want to find the velocity of the astronaut, this is minus m bag, velocity of the bag, over mass of the astronaut equals velocity of the astronaut, which equals minus 25 kilograms times 9 meters per second over 75 kilograms. The velocity of the astronaut in this case is negative 3.0 meters per second. Again, it's just a conservation of momentum problem. Look at the momentum initially, nothing's moving, and the momentum final, and then you set them equal together. So for a third example, now we're going to get into the vector nature of momentum. So you've got two cars running at each other, and they are going to collide, and then this blob is going to go off. Now you have two things you need to know. You need to know theta, you need to know the final velocity. It is an inelastic collision. What does that mean? So let's work this out. So let's start out by looking in the x direction. Momentum's conserved in the x direction, so we broke out momentum into its terms right over here. And you know that in the end they're stuck together, so it's this final mass times some velocity in the x direction. Now the truck is only moving in the y direction, so that's 0. So if we solve for this, now we are going to get mc, velocity of the car in the x direction, initial, over mc plus mass of the truck equals vx. So if we're looking at this, this is 500 kilograms times 10 meters per second over the combined mass, 2,000 kilograms, which is your final velocity in the x direction, which is 2.5 meters per second. Now we're going to do the same thing in the y direction. So now we're going to do this in exactly the same way, except your car has no initial y velocity, so you get mass of the truck, velocity of the truck, initial in the y direction, equals the mass of the car plus the mass of the truck, the combined mass moving, equals your final velocity in the y direction. So this would be 1,500 kilograms times 20 meters per second, all over 2,000 kilograms, which equals 15 meters per second, which is your final y velocity. Almost done. So now, if we are going to combine these, you know that you're going to use Pythagorean theorem, because what you have is a triangle with Vy and Vx. You're interested in this final velocity right here. So you use Pythagorean theorem, you get 2.5 squared plus 15 squared. Your final velocity is 15.2 meters per second. And then if you look at your tangent using this angle theta right here, it's velocity in the y direction over velocity in the x direction. So this would be 15, here we'll make this tangent minus 1, 15 over 2.5, which equals about 80.5 degrees. And double check with tangent to make sure that you're not going off at a funny angle. So this is the final problem. You're going to get a block sliding down a ramp. This block slides down this ramp that is frictionless, collides with this, they stick together, and now they move on to this frictionless part. So what you have to do is you have to break this into 3 parts. You have to go before the collision, you have to go during the collision, and then you have to look at after the collision. Because you know, conceptually, what's going to happen. This has all potential energy, gets converted to kinetic. Okay, we figure out how fast this block is going. They collide. We figure out how fast this total mass goes using momentum conservation, and we figure out how far it goes to stop. So to figure out part 1, before this collision, you know that energy is conserved. We know this is work net, work external equals energy minus energy initial. In this case, no net work, so you get E initial equals E final. Initially, it's just all kinetic energy, mgy. Then it's all kinetic energy, half mv squared. Let's put a little knot right there. Your m's cancel, and this goes to square root of 2gy equals v. If you solve for this, you will get a velocity of 3.13 meters per second. That is how fast block 1 is going when it hits block 2. Okay, let's think about this. Now we're during the collision. We care about this part. In any collision, you know momentum is conserved. So if the momentum at the beginning, I'm just putting this term in here, it's actually going to be 0. They stick together, m1 plus m2. Velocity final. Let's figure out how fast this is going at the end. Now, this has no momentum, so that is 0. So you get m1 v1 naught over m1 plus m2 equals v final. And if you calculate this out, you will get your final velocity is 1.043 meters per second. So this is how fast this conglomerate is going after the collision. And now we care about this part. So let's take a look. What force is slowing this down? This is back to conservation of energy, where your work external equals your change in energy. Now your final energy is 0, no kinetic, no potential because it's stopped. This right here is done by friction, so that is F d times cosine of theta equals negative 1 over half mv squared. And let's take a look at this real quick. This angle, we know friction's going this way, your distance is this way, so this is cosine of 180 degrees, which equals negative 1. So we can cancel that negative 1 and that negative 1. Now we know that friction is mu n times d equals 1 over half mv squared. If you are looking for the normal force, you know that you have this little force diagram straight back from normal 1. It's not accelerating, so sum of forces equals 0, or n minus mg equals 0, or n equals mg. So let's go ahead and plug that in. You get mu times mg d equals 1 over half mv squared. So where does this v come from? It is the initial velocity for this part is the final velocity for part 2. They hit together, they get some initial velocity. So the velocity after the collision is the velocity you plug in here. Let's do some more rearranging. You've got m's on both sides, they go away. So you get d equals v squared over all over 2 mu g, which is 1.043 meters per second squared over 2, coefficient of friction was 0.2 times 9.8 meters per second squared. Your distance is equal to 0.278 meters. And that is a problem using energy and momentum conservation.